All right, here's our video today, the Great Oxidation Extinction, or some people call it the Great Oxidation Event, or the Oxygen Catastrophe, or the Oxygen Holocaust. Some people even called it that. Well, this is when a new type of bacteria, let me write it down, let's get our pen, use white, we'll write it over here. Long time ago, they used to call it the blue-green algae, even though it wasn't algae, but they called it blue-green algae. And this blue-green algae was actually bacteria. And today they're called cyanobacteria. So we're looking at roughly, there's that, maybe 2.3 billion years ago. This cyanobacteria, the once named blue-green algae, they were pumping oxygen into the atmosphere. So if you go back beyond 2.3 billion years ago, Earth's atmosphere did not have oxygen. It had methane, had carbon dioxide, had sulfur dioxide, had nitrogen. I'll write those down in a minute. So the cyanobacteria were replacing this other type of bacteria that use anaerobic respiration. Anaerobic meaning without oxygen. Because with oxygen, the oxygen in the atmosphere would kill this type of bacteria off. So in just a very quick review on this, short review on this, cyanobacteria replaced the anaerobic bacteria because of the oxygen being pumped into the atmosphere, and oxygen would have been poison to the anaerobic bacteria. We'll talk more about that. And by the way, here is the cyanobacteria. Doesn't look too impressive, right? All right, so the atmosphere of Earth, if we go back beyond, let's just go back 3 billion years ago. Why not? So we're looking at an atmosphere that had no oxygen. So it had methane, and this is important, predominantly methane, which you know is a greenhouse gas. It's also a hydrocarbon. You know, to make methane, they call it a hydrocarbon because hydrocarbons have hydrogen and carbon, right? So you would have this one carbon and 4 hydrogens. There's a molecule of methane right there. There's the H for hydrogen. So it had methane, it had nitrogen. We have nitrogen today. It had carbon dioxide in the atmosphere, but again, no oxygen. It also had sulfur in the atmosphere from volcanoes. Should write down sulfur dioxide. Sulfur dioxide, all coming from volcanoes. Now, of course, the early bacteria, the anaerobic bacteria, remember, anaerobic means without oxygen. They wouldn't have lived on the surface anyway. They would have lived deep into the ocean. So we'll make a little box here. Little box. So again, the earliest life forms are anaerobic, without oxygen. And they lived deep into the oceans by these deep ocean vents where we have some creatures living today. And they did not use oxygen. Oxygen would have killed them. There was no oxygen for them to have anyway. There was no oxygen in the atmosphere, and there was no oxygen in the water. And now, obviously, the water is made of H2O, which has oxygen, but there was no free oxygen. So they did not use oxygen. And along came, like we said, around 2.3 billion years ago, aerobic bacteria, the cyanobacteria, which would pump oxygen into the atmosphere and into the oceans, would eventually kill the anaerobic bacteria. Let me clear that out. Go back if you need to. So with this we'll put on one side, we'll have the anaerobic. Let's gotta make sure our pen's working. A little artwork there. So anaerobic, they were heterotrophs. And heterotrophs need to consume other organisms. Consume, like us, right? We're heterotrophs. Consume other organisms. So this early anaerobic life lived deep into the ocean, these ocean vents, very dark world. They didn't need the sun. And then all of a sudden, here comes the aerobic life forms of the once named blue-green algae, the cyanobacteria, and they used photosynthesis. So they were autotrophs, just like plants and some bacteria today. So autotrophs make their own food. And the cyanobacteria were using sunlight, photosynthesis. And so when this event happened, oxygen was slowly pumped into the atmosphere. And slowly oxygen would replace methane. And so that methane haze would slowly disappear and we would get our blue sky. Now, this whole process would have taken about 300 million years. I have another video on what the sky looked like back then, way back then. It was an orange colored sky. You can watch the video on that if you want to know how methane made the sky orange. So anyway, within 300 million years, there would be enough oxygen in the atmosphere to kill off all the anaerobic bacteria. And this great oxidation event would lead to multicellular animals. So in a sense, the great oxidation event, we owe our lives to it. We wouldn't be here without it. No multicellular animals would be here without it. Now, let's clear this out. Remember, methane dominated the world until this oxidation event. So methane, as I said before, is a greenhouse gas. So the average temperature 3 billion years ago, it may have been that high, 167 degrees Fahrenheit. And when the oxygen would replace it, it would cool down to 35 degrees Fahrenheit. So we would get not only an extinction of the anaerobic bacteria and a process that would lead to multicellular beings like us, but we would get the first ice age. And we had 5 so far. The first ice age. We had a temperature that was cooling. The earth was cooling. The first ice age occurred. The oxidation killed off 90% of Earth's creatures, this anaerobic bacteria, and it was the rise of aerobic life. The cyanobacteria started pumping all that oxygen. Methane was replaced. The Earth cooled. The first ice age. And another important thing, that once we had all this oxygen in the air, O3, now we breathe O2, by the way, but O3 is ozone. So this ozone layer would form that would protect us from ultraviolet rays. So there was a lot of interesting things to come out of the great oxidation event. And the most important one is us. That's our video today. Oh, by the way, just to answer one question, again, it's a greenhouse gas because it does trap heat in. So the more methane that is in our atmosphere, the hotter our atmosphere can get, our temperatures on Earth can get. All right, that's it for today.